name is Maya, and I work in the Center for Electron Microscopy and Microanalysis. And today I'm going to talk about the environmental scanning electron microscope from Thermo Fisher, which was previous FEI and even that Philips. First of all, what is an environmental electron microscopy? This environmental means that you're observing the specimen in its native environment. So that could be either the solid gas or solid liquid interface. We usually do SEM or TM electron microscopy in the solid vacuum interface. So why do we need vacuum? Because if we have high pressure, so this, for example, are molecules of water or air, and this is an electron, it will be scattered around, and we cannot move it over large distances. We also want to prevent beam-induced chemical reactions. And if we have low pressure, we achieve that. The low pressure is also needed for the stable emission because you put 20 keV in the SEM and in the TM 200 keVs. So you can have arching. And it's also needed for, we will see that later, for some detectors and lenses. We also want high vacuum because we want to provide a clean surface for the coating deposition also and surface analysis. I'm sorry, I'm also putting new participants in. So environmental scanning electron microscopy is divided into 4 groups. We have the ESEM, which is an open cell with differential pumping. And we have the low vapor pressure liquids that can be observed in the normal SEM or TM by using ionic liquids. If we have a closed cell, this is popular in the TM, but also it's possible also in the SEM. You have different abbreviations, so the liquid SEM, liquid cell SEM, or wet SEM, or you can use a special membrane that you insert below the pole piece, and you can image native environment. This is sometimes called atmospheric pressure SEM or air SEM. So as I explained, we have this one, the open cell, with differential pumping and special pressure limiting apertures. So we will go into details about this one. First, what is an ESEM? The SEM principle was introduced by introduced by Zotkin in 1942, but it had really low resolution until Oatley and his group, the Everhart and Thorney, they worked in the group, produced the first commercial SEM. And the ESEM was invented, we could say invented by Danilatos, because he commercialized the ESEM. I have something missing here. So he was from Australia, and they wanted to analyze the wool, which was wet, oily, and dirty. So the ESEM definition is that the microscope can achieve in the column where you have the sample 600 Pascal, which is about 5 torrs, at 0 degrees Celsius, where you can have 100% gas phase of water, for example. And an ESEM, the other definition is it has multiple pressure limiting apertures and an environmental SEA secondary electron detector. So it has a special detector and different apertures. So this is a variable pressure system. We work in 3 different areas: high vacuum, low vacuum, and the ESEM. So you will have it noted here, and you can choose only water to insert in the chamber. The normal rotary pump is in the other room. Below here is a turbomolecular pump. Here you have a differential pumping. You have a manual valve, which you will be using. And here you could see the water that is introduced inside the SEM. A quick overview of the SEM. It's really simple. It's the same as any SEM. So you have the gun, you have the condenser system, you have the objective system with the scanning coils, and here you have the chamber with the sample and the detectors. what is a really neat thing here, we have only one fixed aperture, so no need for wobbler alignment or yeah, wobbler. A quick overview of the detectors outside. This is the EDS Live, Aztec Live, Ultimax detector, SDD. And this is the manual valve, which you will use if you operate in low vac or ESEM mode. This is a nav cam. Unfortunately, we have some problems now with the nav cam, but we'll get it fixed. Why is it really useful? Because you get an optical image and you can save the coordinates where you did the analysis, and you can then correlate that with the images. It's really fast. And similarly, the EDS has a possibility to import an optical image either from your phone or something like that, and you can also correlate that where you did the analysis. The inside of the SEM looks like this. This is the turbo pump. Below that, here you have the CCD camera for viewing of the chamber. Here is the Everhard-Thorny detector, the concentral backscatter detector. The EDS detector is here. You don't see, but there's a large field detector hidden back here. You could see it if you look below it. So this is the large field detector. Or an easier way is to do a mirror effect in the SEM. So you can see the concentral backscatter detector, the Everhard-Thorny detector, the EDS, and the large field detector. You will mainly have to remember this photo because it's in the one of the quadrants. So you have to check that the large field detector is inside, the EDS is inserted, the backscatter detectors here, and for the secondary. Also, the huge table can fit 16 pin stubs, and you have a large area of for samples, so 6 centimeters, big samples can go inside the chamber. This table is also for the beam deceleration. I see here, yeah, I'll tell that later. Okay, so some of you have never operated a scanning electron microscope. So what is an SEM? So it's scanning through every pixel, and that's how you get an image. In every pixel, you collect your either secondary or backscattered electrons. So this is a pixel, and you have multiple pixels, usually 1,000 and 900. And you save it as for example, an 8-bit, you have 265 shades of gray inside. We just now talk about this, but later we'll talk about the interaction volume. One thing that's important is the magnification. What is this? This is the scanning distance on the image divided by the scanning distance on the sample. So this is a lower magnification, scans larger area of the sample. This is a higher magnification because it scans a smaller area of the sample. But this is true if you don't have any charging. If you remember the mirror effect that you get on the SEM, the magnification is not correct, or the scale bar. When you have an SEM image, you never look on the magnification bar. You usually look at the scale bar because if you rescale the image, the scale bar is rescaled, the magnification stays the same. So if you compare the 7600F and Quanta, Quanta has a 3.5 times higher mag number, but that doesn't mean it's the same. So yeah, you have a conversion that you need to be aware of. And this is similar on many microscopes from different manufacturers. The resolution depends mainly on the microscope, the sample that you have, and how good is your beam alignment. Why well, so magnification is nothing if we don't have the resolution. So the resolution means you're making the spot smaller. Um, Ideally, you want to have it 0, but that's never going to happen. And in our Quanta, we have a tungsten source, so this is not similar to a fixed source. You can vary the spot size on the Quanta from 1 to 10, but this is for higher, this is not for higher magnification. This is for example, for some samples that are higher, 1 micrometer or more to be seen, so not nanometers. So you can change the probe current. So this means how many electrons you have, and you can change the electron energy, how much energy they have. You will also be changing this to get a view of what is going on in the Quanta. So this was done by Mattia. So this is a resolution test to see that the Quanta operates in all the specifics that it's supposed to be. But again, you can see the magnifications here are higher. This isn't meant to be, I mean, you use a Various or the 7600 for higher magnification. This tungsten based is not meant for the high magnifications. And then also its resolution is dependent on the sample. So this is a standard. This is gold on carbon, which is ideal. So usually we don't have those kind of samples. And it's a thermionic SEM. So now the beam alignment, I've divided this in 4 steps. So first you will be aligning the source centering. So you align the gun on the condenser system. So this is the condenser system. I don't know if anybody used it on the 7600F, but this is in, it's quite tricky because you're looking for the brightest image and not a lot of people use it. On the Thermo Fisher Scientific, this is really good because what they do, they use the deflector coils, which are located here, and they turn off the scanning coils. You have an aperture here, and you're scanning with the deflector coils above the aperture, and you look exactly at the aperture. Because the coils in the Quanta are not, deflector coils are not that good because it's thermionic based. This is not a circle, and this is not astigmatism. This is just how it operates. And this is a sample that was contaminated. So you could see it should be round, but because of the deflector coils, it looks like an egg. Again, the deflector coils are not good. You will see a circle on fib or Various. Then the 3 other points that you align is the focus, astigmatism, and the wobbler or lens modulator. So the focus, you're just changing the current in the objective lens. Well, ideally you would have no aberrations, but you do. So you look like this. So you use special apertures to cut the high angles. Here we have only one fixed aperture, and this is kind of neat because you don't have to align it. But still, because we have problems in the lenses, you have astigmatism that needs to be correct. So you will learn the procedure if you are not already a user, an SEM user. So again, back to the pressures. The high vac is just normal SEM. In the low vac, you use it for non-conductive samples where you have only one pressure limiting aperture, and this is here in the area of the vacuum. If you want to use the ESEM mode, this is meant for wet samples where you put another additional pressure limiting aperture or an additional detector that has also a function of the aperture. Again, by definition, this is achieved at 600 pascals. So how does it work? The high vacuum has everything under high vacuum. It has a rotary pump and a turbomolecular pump, and here are the samples. Again, the source, the condenser objective, the differential pumping, and the chamber. Here you have the water where the valve is closed. When you operate in the low vac, you actually heat the water and you have water vapor coming inside the chamber. Because some can get inside the column of the SEM, you have an additional valve which you will open manually. And this is the differential pumping. So it pumps in this area. This is the pressure limiting aperture. So it's 200 micrometers. If you work in the ESEM mode, you have to mount an additional aperture. And you select it here, either this one or this one. You then the same goes. You open the valve, the water vapor comes in, some can get inside the column, and you pump it by the diffusion pumping system. Okay, so the detectors that are in the standard operation are the large field detector, the concentric backscatter detector, the Everhard-Olney detector, and the EDS detector. This means that you can use the SEM, the Quanta, in the high vac and in the low vac, so for conductive and non-conductive samples. For the high vac, you use the Everhard-Olney and this one, the backscatter detector. But in the low vacuum, you cannot use the Everhard-Olney because here you apply a high potential, so you speed up the electrons, and this can arch over if you have low vacuum. So you use this one, large field detector. So again, you will always remember this image on the CCD, so you will know which detectors you have. The electron beam solid interaction. Okay, you have the primary beam, which are your electrons, and they hit your sample, and what you get out of the sample are electrons, Auger secondary backscattered, and you get photons, X-rays, cathodoluminescence. What is the importance here? So if you don't have a conductive sample, you can have charging on your sample, and you can have a positive or a negative charging. So this depends on what you put on your beam. So for example, if you have 1 picoamps flowing for 1 second, this means you have 6 to the power 10 to the power of 6 electrons every second. So your electrons cannot flow through the ground and they stay on your sample, which means that they will accumulate on your sample. This will produce an electric field, and this can be so huge that you can deflect the beam and scan the top, so you can scan your SEM. This is kind of neat because you can, if you don't have, like on the Quanta, to open the chamber to see the inside, you can see where are the detectors. So this is the Geol 7600F. You can see the VDS, the EDS, the lay detector, and you can see the backscatter detector. So sometimes it's useful, usually it's not useful. You have the deflected beam, deflected secondary electrons, increase of the emission, sample drift, and a problem in the X-ray signal. Again, note that the scale bar is not correct because the definition of the magnification is how much you're shifting. Well, this actually shifts a lot more. Specimen damage, there are a lot of damages that you introduce. So you can have the electrostatic charging, you can have hydrocarbon contamination, heating, and radiolysis. So now we talked about the image formation in the SEM. So it's from pixels. You scan from each pixel to each pixel. And here you have, you take either secondary electrons, which are from the top surface, or backscattered electrons. What is kind of neat is the interaction volume. So if you use 20 keV in the gold sample, you go almost to 500 nanometers. If you use 2 keV, you're really scanning the surface. By definition, the backscattered electrons are the primary beam that undergo multiple scatterings. And you can use a lot of free softwares. The Casino is really useful, where you can see that in every dot, there's an interaction happening. So in those interactions, you also have secondary electrons coming through. Yeah. The secondary electrons are the electrons that are generated by the primary beam, and can be divided into different groups. The primary beam is the number 1. The backscattered, so like this, are the number 2. And by definition, the secondary electrons are lower energy, so below 50 eV. Sorry, secondary electrons below 50 eV. The backscattered are between your primary beam, for example, 20 keV, and below that. So if you use a 2 keV, you can see the interaction is quite smaller. If you zoom in, you can see that there are a lot of interactions. The secondary electrons, you note them as what is important in the secondary electron is the yield. So why we use, for example, golden coatings is because we have higher yield for secondary electrons, and because it's not that thick, it gives us better images. So for example, carbon, the yield is really low. For gold, you see the yield for the secondary is here, and for the backscattered, it's here. And that's why you can see the contrast in the backscattered image. But here I would like to know that this only applies if you go to higher voltages. So when you're on 1 keV, 2 keVs, that doesn't apply because the physics of the cross-section is different. An animation, what happens? So you have an electron, it hits out the outer shell electron. This is a secondary, for example, and the backscattered, because of the nucleus, it changes direction and it goes under multiple scatterings, and it comes out of your sample. Okay, not really that important. So the secondary electrons have the high resolution. They are topographically sensitive. Little element sensitivity, which we saw, and they're really sensitive to charging. This is a sketch of the detector, which is in the column and in the chamber and in the column. This would be like in the 7600 lay, and this one is the say. The bias voltage attracts the secondary electrons that have low energy. So your image will be really nice. You can see where your detector is positioned because you can see it's brighter on that area. When you have an in-lens detector, you actually need a magnetic field or electrostatic field to push the electron back in, so it goes inside the detector. In that case, you don't see such a nice image because you don't know where detector is positioned because of the Lorentz law, because this is the notion of the electron, but you can get higher magnifications. And okay, so at the edges, you get more secondary electrons. And this detector is on the Quanta 6650. And this detector is similar to the old SEM that we had. The secondary electron images change depending on your accelerating voltage. As we said, that if you use 20 keV, it goes a lot more deeper, and this is the image. So this is a flake which can be seen with lower voltage, and vice versa. If you want to see something below it, you put a higher voltage. And again, for the chips, if you want to see the contacts, higher voltage. The backscatter detector, it has a lower resolution and it's less sensitive to charging, but it can give you an atomic number contrast. So if you have different materials, you can get different backscattered coefficient, and you can see this in the compo image or the BSE image. In the 7600, we have a left and a right side. That's why it's called a topo and a compo. And your backscattered is, your primary electron is backscattered into the solid state detector. And you have different segments. If you sum up all of them, you get a compo. If you divide B minus A, you get a topographical image. The same applies on the Quanta or the Thermo Fisher. Here you have concentric rings. The inner ring is more for the compositional. The outer rings are more topographical. Or if you change, if you take all of them, you get even more signal. The detectors for the large field, the detectors for low vacuum and ESEM mode are the large field low vacuum detector, and the gases secondary electron detector, which is this one. How does this work? So the large field is usually inside the chamber. If you want to work in the ESEM mode, you put an additional aperture. This one is actually containing an aperture inside the detector. The large field detector and the low vacuum, how does it work? So you have your primary electron that hits your sample, and because you have molecules, you cannot use Everhard-Torni because it would arch over. But your secondary electron is still generated. You apply a bias potential, so you track those electrons. And because they ionize really quickly your water molecules, you get an ionized molecule and you get an additional electron. And this electron, again, ionizes and ionizes. And you get more and more electrons coming to your detector. So those electrons are then acquired. You see what your topographical image is, but you also have your positive ions now here because they lost electrons, and those are attracted to your surface because you have negative charge accumulation here, and they take your electron, and you don't see the charging anymore. So in the high vacuum, it's for the conventional SEM for conductive samples. In the low vacuum, if you want to use non-conductive samples and observe them. In the ESEM mode, it's usually for wet or moist samples. Materials that can be characterized are different. You can characterize metals and alloys, and because you have four magnetic samples. You can observe also magnetic samples because your lens is not inside the chamber, inside the sample. You can analyze ceramics, composites, plastic, films and coatings, geological sections, materials, soft materials, polymers, and some particles. But again, this is a thermionic-based SEM, so not nanoparticles. There's so your samples has to be firmly attached because they cannot fly out the holder. You can damage the turbopump or the inside of the SEM. So the samples need to be stored in a dry, dust-free environment. So you also don't want to degrade the image. So these are some examples from the first trainings that we have had. This is the CCD image of the magnetic sample and the NavCam. You can easily see on the NavCam where you want to do an SEM analysis, and you can correlate that with the images. The polymer here is from Ateca. It's non-conductive, and you want to use it in the low vac. So this is a topographical image, and this is a compositional image. A magnetic drill, again, you can put huge samples inside the Quanta. And a fly and a piece of paper in the ESEM mode because this was wet. So the sample have to be fixed, no moving parts. You can damage the pump or the column. So there are some adapters that you have to buy. They're the same as on the FIP or on various. So about the microscope, when you will come, you will see that you work on the main PC. This is the user interface. And never put the USB in the main PC. It's connected to the support PC where you can insert an USB, but we rather save the images on our server and then you take them out, down from the servers. This is also an EDS support. You have two keyboards, but you can use only one if you want. So for new users on the Thermo Fisher, you have the server, which looks like this. When you double click on the green one, the server opens and you can start the graphic user interface. So show user interface, and this is the user interface. You have the title bar, the menu bar, you have the toolbar, 4 quadrants, and the first one is normally for the secondary electron image, the compositional image, NavCam, and the CCD. The pages and modules are here, and it's really easily represented. So the detectors have the eye, this is for the electrons, and this is for navigation, stuff like that. This is for the beam deceleration and alignments. Above them are scanning presets. This is like photo 1, photo 2, slow scan 1, 2, for example. In the menu bar, you will see that you can find a lot of things. So file, edit, everything. So we will skip this because you will do this on your training. The toolbar, if you double click it, it moves to a round number. This is really useful. You have some tips and tricks that you will learn on the training. The modules that we explained, the 6 modules are explained here. So here we have the alignments, but it's really easy to find, yeah. For those who are used to the GEOL system, you have the joystick and the manual user interface. But for others, you will use the mouse. So when you come to the microscope, you will check that the microscope is on. This is the green light. Then you will check the notes in the logbook. Then you will check what you log into the microscope and see what on the graphic user interface, if there's any errors or anything like that. So we'll do that actually on the training. Here, I wanted to put the standard condition that we kind of agreed on. It's not necessary. So we said that, well, we will leave the voltage to 10 kV. This is not necessary, but I think it's good because a lot of users are kind of used to have standard conditions. So voltage and spot, what is really necessary is if you take any detectors out, put them back in, and the beam deceleration table, the EDS is inserted and cooled, and put the lookup table on normal. So if you apply brightness contrast on your images, put it back to normal because this kind of some users are not used to changing that. And if you change, for example, your name here, if you change, it's usually on the CMM, but if you change it, please change it back, because then we have some people working and they, at the end of the session, they see that they were working on some other name. On the EDS, you will have your own save conditions, so you will have your own username. So this is open for discussion. For if you have any um, ideas, just tell me about them. Okay, so venting, you just observe, look at what the vacuum is, and then you click vent. It's venting on air, so it's kind of noisy, but okay. The doors, you have to open them gently. The whole chamber opens. You can put 16 pins, so it's really user friendly. Okay, on the navcam, we will do that on the training, but if you put it on the 10 mm marker, you will get a nice image. Unfortunately, this is not happening because we have a problem, but it will be fixed. So if you use it below or above, you don't have a nice image. Okay, and before you start the session, you always check that the beam is off. So yeah, we will do this on the training. So what I want you, well, the goal for the training will be not to damage the source. So the manual valve for the low vacuum, don't contaminate the column, and don't damage any detectors. So this is on the old microscope. You have the CCD camera, so I think this won't happen. For now, only the SEM, and I think we will train also Katarina and Drnoshek to change the detectors, because you can easily damage the EDS, which is really expensive. Some abbreviation. I would advise not to use the low LV SEM for low vacuum, because it's kind of messy. The low voltage SEM by Joy and Joy is the same abbreviation, and because variable pressure is really nice abbreviation, I would advise you to use this one. And okay, this is the time to say thank you for everybody, for everyone that helped me learn more about the SEM. And for those who will be starting the trainings, we also have our old microscope, all the parts that you can see. And if you want to learn more, you just tell me, and we can go through all the parts: the gun, the aperture, the stigmators.